LED matrix schematic diagram. This is the connections to the MXP connectors. The rows are on connector A and the columns are all on connector B. VI is running at this point, and initially the auto pattern switch is engaged, and you can adjust the pattern loop time right here. Try different speeds here. Once you start getting below 100 milliseconds, you'll start to see interesting phasing effects because the speed is starting to be similar to the raster update speed of the display. I'm going to put this into manual mode. The flashing that you see here is an artifact of the video capture. It really appears stationary to the eye and flicker free. The specific pattern of the 2D Boolean control is captured by this single 64-bit hexadecimal value. You can set up a desired pattern and then copy and paste that value into the pattern codes array back here in the auto pattern generator loop. For example, let's see how this particular value FF81 etc. was created. I'm going to take a moment to adjust the display. And you can see that this hexadecimal value is the same as what is located in the array constant. Alright, I'm going to stop the VI and take a look at the block diagram details. This block diagram features three parallel loops. We have the pattern generator, the main loop, and then a high-speed loop to drive the raster style display. This is using a timed loop for more precision. Everything ends with a little bit of cleanup here at the end. Alright, I'm going to begin with the high-speed loop. This is a timed loop. I'm using the 1 kilohertz clock and a 1 millisecond period. This code takes care of opening up channels to the digital outputs. These are found under MyRio Advanced I/O, Digital I/O, making use of open, write, and eventually close. Now these can work on multiple DIO channels at once. For example, here I'm setting up all 8 rows. Here's the green columns, and here is the red columns. That way I can keep them distinct from each other but yet related. Here I'm using merge errors to group those 3 error clusters together into a single error cluster heading into the loop. Now everything begins by disabling all of the row drivers. Here I'm setting all of the row driver lines to a high level. After that, update the green column drivers, update the red column drivers, and then finish by updating the row drivers. That code executes relatively quickly, leaving the balance of the time to display the actual LEDs. Now it's important to alternate the green and the red columns, and this structure based on the feedback node and the NOT gate, if you will, gives an alternating true-false sequence. So on each pass of the loop, you first get high or a true, and then you get a false. Now inside the true subpanel of this case structure, I'm deactivating the green columns and then activating the red columns. This section right here gives a sequence running from 0 to 7 and then returning back to 7. Here I'm picking up the red matrix from the main loop, which is a 2D Boolean array, and then picking out the necessary row, which eventually gets applied to the red column drivers. Looking under false, it just flips it around. Here's where I'm working with the green columns, and the red columns are inactive. Now in every single pass of the loop, there is a write to both the green and the red column drivers. But again, this case structure essentially flips back and forth whether or not you are applying a useful activating pattern or something that's disabling all the drivers. This section handles walking the low-level value from one row to the next. I want this to update every other loop pass that allows the green and red to alternate for a given row. All right, let's look at the main loop. This is a global variable used to communicate from the main loop to the high-speed timed loop. If you double-click on the global variable, it opens the VI. This is a special VI that does not contain a block diagram, but only a front panel. And here I have set up a number of 2D Boolean arrays. You can create a global variable from scratch this way. Look under the programming subpalette, place the global variable, double-click it, and that opens up a new VI. Now supposing I wanted to make a numeric control. Simply place the numeric control, give it a meaningful name. This is maybe not so meaningful, but the point is you can name it. You can also have multiple variables inside that VI. You go ahead and save the VI. I'll use the default name of global2. Close that down. And now I can click in the middle of the global variable and select the desired variable. Again, we only created one here, so there's only one available. Now at the moment, it's intended as a destination. Here it is a source of information, so you can change the direction of the global variable. Now if I were to copy the existing global variable, we see that there's 4 possible options, and that's where I can get the needed green matrix and red matrix in the main loop. In a similar way, the global variable called green pattern links back to the slow speed loop back here in the auto pattern generator. Now let's take a look at the 2D Boolean control. This is the one called green. You can make one of these from scratch this way. I'm looking under silver, looking under array, and then I will pick out the array. At the moment, we have just a shell or empty array. We need to give it a specific control. Look under Boolean, look under buttons. There's actually quite a number there. I'll just go ahead and go with blank. Going to select the button and then resize that to make it a little bit smaller. Let's try going with 20 by 20. All right, that looks pretty good. Next, I'm going to tug on the array frame to expand and see more buttons. Add dimension. That makes it into a 2D Boolean array. I'm going to turn off the index display, and then once you start clicking on the buttons, that defines the outer extent of the Boolean array. You can also select any desired color. Let's try setting the button color to blue. All right, let's next take a look at the pattern indicators underneath each of the green and red 2D Boolean controls. Here's my 2D Boolean array. I reshape that into a 1D array of 64 bits, reverse the array, pass it through Boolean array to number, and that gives me the numerical value that you see underneath. Need to get this running again. Let me illustrate this starting with my blank grid of buttons for red. Blank would correspond to all false, and the pattern is 0. Now I'm going to activate some values in the first row. These are associated with the first byte in that hexadecimal value. Here's the least significant bit and a couple adjacent bits. Again, that would be the last byte in that 64-bit integer. Now the nice thing about these pattern values is you can select any arbitrary collection of 64 bits forming your pattern, and then you can simply copy and paste that value into your pattern codes array back here. Now pattern codes is based on stepping through that pattern codes array. It essentially undoes the earlier operation, forming that back into a 2D 8x8 Boolean array, and then sending that as a global variable to the main loop. All right, let's take a look at stopping these 3 parallel loops. I have a single stop button associated with the main loop. The mechanical action is set to switch when pressed. Now back in the auto pattern loop, I have a local variable. I'll show you where to find that. A local variable can be associated with any of the front panel controls or indicators. I'm going to change that to read, and that's the mode that's being used right here. Now, when you press the stop button, that is instantly communicated to this loop, and that stops the auto pattern loop. In the same way, when that stop button is pressed, that fact is communicated to the high-speed loop over here. Now, an air condition also can terminate the high-speed loop. Here I'm using a true constant and the same local variable, but now in write mode, so that an air condition breaking us out of the high-speed loop would effectively be communicated back to the main loop as kind of a virtual press of the stop button. Now, the final piece of shutdown code at the end needs to know that all three loops have successfully stopped. And I'm going to do that with the usual propagation of the air cluster technique. However, the two slower speed loops do not have any VIs at the moment that generate an air cluster. So that's how you can create one from scratch. These are all merged together along with the air cluster from the high speed loop, pass that through the simple air handler, and then terminate at this flat sequence structure containing a local variable for the stop button set to false. And that effectively unsticks the button. Without that piece of code, you would stop it and then the button would stay clicked. I'd like to wrap things up by mentioning that the high-speed loop is going at 1 millisecond per pass. The main loop is at 100 milliseconds to give a fairly responsive front panel, and then my auto pattern generator is operating at this variable loop time. Turns out that the logarithmic mapping gives you a more useful control, and you can take care of that under scale and then mapping, and then set that to logarithmic.